Hello everyone, I'm Anish and today we will be studying about the CMOS buffer. So we will do the complete analysis of a CMOS buffer, basically the pulse response and a ramp response, and draw the transfer characteristics for voltage, right? So before going to the CMOS buffer, first we'll just get a brief idea what is a CMOS inverter. I hope you have already studied it. So basically a CMOS inverter, right? It does is basically that when the input is high, right, when the input is high, the output wants to go all the way down to this point, right, to this 0 volts. And if the input is low, right, then the output wants to go all the way up to this VDD, right? So what is the symbol for a inverter? So for an inverter, right, let me draw this. So let me draw this in rough only. So this is basically an inverter. So when the input is high, then the output will go low, and when the input is low, then the output will go high, right? So this is basically what a CMOS inverter does. Okay, now this is the voltage transfer characteristics of a CMOS inverter. So there are different regions here. I hope Himanshu has uploaded one video on CMOS inverter. You can check that out. Here just I will tell you the regions, like in what regions the PMOS and the NMOS are present. Like between 0 to VTH, right? Between 0 to VTH, we can see that if the input is between 0 to VTH, then this PMOS, right, the PMOS will be in linear region, and the NMOS, right, NMOS will be cut off. Why? Because this NMOS won't turn on because VGS will be less than its threshold voltage. That's why this PMOS will be in linear and NMOS will be in cutoff. Okay, so you can see it for yourself. So solve it. This is a very standard circuit. You can solve it. Okay, and all the other regions are present, but most important is if the input is low, our output is high, and if the input is high, then the output is low. That is the most important point to be noted. Okay, so now let's solve for the CMOS buffer, right? So how do we get the CMOS buffer? Basically, if we interchange the PMOS and NMOS of a CMOS inverter, we get the CMOS buffer, right? So this is the basic structure of a buffer, but what is the issue with this is, like in this case, right, if the input is high, right, what should a buffer do? It should also provide high output. It does provide high output, but it doesn't go all the way up to VDD. Or if the input is low, it doesn't go all the way down to 0. Why and how we'll show later on the slides, right? So let us first understand what is a buffer, right? So buffer basically, let me write this, passes the input, right? Buffer basically passes the input. Okay, what is the symbol of a buffer? So symbol of a buffer, right, is something like this. So if our input is, let's say if our input is high, then output will also be high. And let me copy this again. If our input is low, right, then our output is also low. Okay, so this is what a buffer does. Now let's understand a few basic characteristics of a buffer. So for the buffer, right, it has high input impedance and low output impedance, right? So you will I hope you have learned this, or if you haven't, you will learn this in basic analog circuits course or something. Okay, so a buffer has high input impedance and low output impedance. Okay, why do we use the buffer, right? The reason for using the buffer is basically to eliminate the loading effect in the circuit to the next stage, so that the next stage doesn't load the present state, right, present stage, that is. So yeah, all of these things you will study. Just I have to mention what is a buffer. Now let's do the analysis of CMOS buffer with pulse input, right? So in this case generally what happens is impulse input, the initially it is 0, then it goes to high, but here we're starting with one like high voltage only. The reason is simple. For better understanding and for easier like analyzing this buffer circuit, we are starting with 1 volts. Okay, so yeah, this is like VDD is 5, VTN and mod of VTP are same, which is 1 volts. And one thing is that the T, right, the time period of this waveform is very high. Okay, so let me mention this. T is very high. Okay, high. So yeah, that is one thing to mention. Now let's do the first case between 0 to T by 2, when the input is between 0 to T by 2. So what is the input in that range? The input is VDD, that is 5 volts. So case 1. When the time, right, it is between 0 to T by 2. So in this region the Vin is basically 5 volts, it is VDD only. So let me take the circuit again. So here with the circuit, so first thing what we have to assume is that there is a parasitic capacitor at the output node. So this will help us to analyze the circuit, right? So let's say this is a capacitor or capacitance C. Now what is the voltage of the input? Input voltage is 5 volts. So what is the, like, let's assume the initial charge is 0 across the capacitor. So V out is initially 0, the source of this NMOS is 0 and gate is 5. So what will happen? This NMOS will turn on, right? It is more than the threshold, and this like gate of this PMOS, right, is higher than the source of this NMOS. So this PMOS will be off. So VGSN is greater than its VT, right, VTN. So NMOS will be on, and VGS, sorry, not VGS, VSGP is greater than, no, it is not greater than, like it's less than its mod of VTP. Basically it is negative, right? So PMOS of, what is the value, right? What is the initial value? So I can also write that also here. Basically let me zoom in a bit. VGSN at 0 plus, right? What is the value of VGSN? It is 5 volts only. And what is the VSGP at 0 plus? It is minus 5, right? Minus 5 volts, because this point is 0 volts and this one is 5. So VSGP is minus 5 volts. So yeah, PMOS, you can see it is off and NMOS is on. Okay, so now we have to check, is it in saturation or is it in not saturation? So like one thing we can avoid, like doing that overdrive voltage calculation, right? The source voltage is always common, so we can ignore the source voltage calculation. What we can do is simply just check whether this drain voltage is higher than the, like whether this drain voltage is more than one threshold down than the gate voltage. By that, what do we mean? Basically this VD, right, VDN should be greater than VGN minus VTN. Okay, by this, if this condition is true, then this MOSFET NMOS will be in saturation always. So will be in saturation. Okay, so how do we get it? Basically nothing, that simple equation only, VDS greater than VGS minus VT, and the source voltage cancels each other out. So we are only left with this drain voltage, right? Drain and gate voltage. So yeah, we can simply check these two voltages, right? So what I can observe is this VDD, right? This VDD is 5 volts only. This VDD is 5 volts only. So yeah, this VDD is more than VG minus VT. So this NMOS, if it turns on, right, it will always be in saturation region. So yeah, this NMOS is in saturation region. Okay, so like what happens in saturation region, the current follows square law, and like there is some constant current flowing through the this NMOS, and it will charge the capacitor because this PMOS is off. So this capacitor doesn't have any discharge path. So let me first draw the circuit. Like this is 5 volts only. Okay, and this is the NMOS current and this is the capacitor. Okay, so yeah, and this is the V out, right? This is the V out. Now one thing what we have to notice is, like in the CMOS case, right, CMOS case, the the VGS doesn't change, but here it changes, right? That makes the analysis a bit difficult. So what is happening here is, yeah, this current is flowing and this capacitor is charging, right? So V out is increasing. And what is V out? So V out is increasing. That means the source voltage is also increasing, right? Source voltage is also increasing of the NMOS, so the VGS is decreasing, right? VGS is decreasing. So what will happen? The rate at which this this will charge, right, will reduce. Why? Because remember the current equation, it is VGS minus VT whole square. So VGS is reducing, so the current will also reduce. So this IDN will also reduce. So the rate at which it will charge will reduce, but obviously it will charge to its steady state value only. What will it get charged to? So for that we have to go to the steady state value. So for that we have to find the condition until when the NMOS will be on, right? Because PMOS is anyways off always. So only when the NMOS is off, then the capacitor will be reached steady state and it won't discharge and charge also. So the voltage across it will remain constant. So NMOS will be on when the VGS is until the VGS is greater than its threshold voltage. So the VGS of N should be greater than equals to the VTN, right? VTHN. So what is the VGS? VG is 5 volts only. And what is VS? VS is the output voltage. Okay, it is the output voltage. And yeah, let me write this better. Greater than equal to VTHN. So what is VTHN? It is 1 volt in our case. We have taken the example. So V out, right, is less than equals to 4. So up until 4, V out will keep on increasing. But after 4, it won't go above 4, because after that what will happen? This NMOS will be off and the current will be 0. So this capacitor won't have any path through charge, or also the PMOS is anyways off, so it won't have any path to discharge. So let me just draw the graph. Like obviously this won't be perfect graph. Okay, so this is with respect to time axis, and this is the, let's say this is the V out. So what is happening? This isn't linear. Okay, this won't charge like this. But in the books it may show linear, but we can approximate it like linear, but in actuality it isn't linear. What is happening is, this is charging, right, but the rate of charging is slowing. Let me draw this bit. Charging is slowing and it reaches steady state. Now it remains constant. Okay, it remains constant until T/2, that is. After that we'll see what will happen next. So here, what is the voltage? The voltage is 4 volts only. 4 volts. Now what does this 4 volts mean? Basically this 4 volts basically means VDD minus VTHN. Okay, so yeah, when the input is high, right, input is high, here the input is high, right? If the input is high, we are saying that output is also high, but it isn't exactly all the way going up to VDD. It is going VDD minus VTHN. So this is the case 1. Now we'll go for the case 2. So like what is happening at the case 2, right? So let me first write case 2. So case 2, right, it is between T/2 to T, right? So in this region, what is the V in, right, the input voltage? So the input voltage, right, V in is 0 volts. V in is 0 volts. So let me first take the circuit again. I have the circuit copied, I think, but this time we have one initial condition, right? The capacitor is charged to 4 volts and this is 0 volts only. Okay, this is 0 volts only. So and this is 5 volts. this is 5 volts. So what is happening? So this is 0 volts and this is 4 volts. So this PMOS will turn on because VSG is more than its mod of VTP. Mod of VTP is 1, and this NMOS, right? This NMOS will be off because this is 4 volts. This source is higher than the gate, so NMOS will be off. Simple. Okay. Still I'm writing NMOS of VGSN equals to minus 4 volts and PMOS on SGP equals to plus 4 volts, right? So that's why this is on and this is off. Okay, so is this PMOS in saturation? So in this case also we can simply check that the source condition, right? So source will again get cancelled out and we will only be remained with the drain and the gate. But this time I will write down the equations so that you will understand it better. So for it to remain in saturation, right? So the VSDP should be greater than equals to VSGP minus mod of VTP, right? So yeah, the source cancels out, so we are left with this VSGP plus mod of VTP is greater than equals to VDP. So what is the gate? Gate is like, let's say gate is the input, right? Gate is the input, should be greater than equals to, what is the VD? VD is always 0 for this PMOS, right? VD is always 0, so it is 0. And what is the VTP? VTP is 1 only, minus 1. So VN has to be greater than minus 1 for it to remain in saturation, which is the case, right? Vn is 0, so Vn is more than minus 1, hence yeah, this will always remain in saturation. So if like we pass the threshold, right? If VSG is more than VTHP, then it will always remain in saturation. So again, say the same analysis. If this is in saturation, what will happen? This will be replaced with a current source basically. So yeah, let me replace again a current source. So the NMOS is off, right? NMOS is off, so obviously it will get a discharge path. The capacitor, that is, this was charged to plus minus 4 volts. This is V out. So this capacitor will discharge through this current source, right? This capacitor will discharge through the current source. To how much will it discharge to? So when will the PMOS be off, right? PMOS will be off when the VSG is less than the VTH, or it is equal to the VTHP. So VSG has to be always greater than equals to mod of VTHP, right? What is the source voltage? Source voltage is V out only. What is the gate voltage? It's input and it is 0 only, so it should be greater than equals to mod of VTP, which is 1 volts. So it will go until 1 volts. After that, what will happen? It will turn off, right? The PMOS will be turned off. So this capacitor, right, it won't have any discharge path, so the output voltage will go down till 1 volts and then it will remain at 1 volts. So how will the graph look like? Again, I'm drawing the rough estimate. Again, let me take this graph. So again, it will like reduce not linearly, because again, what is happening? The VSG is changing, right? VSG is changing because the source is reducing. The source is reducing again. The gate is constant, but source is reducing. So in the current equation, the ID will reduce again. Okay, so that thing you have to keep in mind. So yeah, this is reducing, and yeah, this will go to 1 volts, and this will remain at 1 volts. Okay, 1 volts. So is this the like this will repeat or not? So for that we have to do a case 3, because yeah, the first cycle, right, the first cycle won't repeat. This cycle will repeat, but the first cycle won't repeat. So we will do the case 3. Also, what does this 1 volt signify? This 1 volt basically signifies that this is mod of VTHP. Okay, so this voltage, right, upper voltage will go all the way down to the threshold voltage of the PMOS, right? So yeah, now let's do the case 3. Case 3. So case 3 is T, capital T to 3T by 2. So again in this region, right, in this region Vin is basically 5 volts, right, 5 volts. So again let me take the circuit, this circuit, right, but this time we have one difference, that the capacitor is initially charged, right. So let me take this circuit. So what is the capacitor charged to? It is charged to 1 volts. 1 volts. Sorry. So if it is charged to 1 volts, what is the VSG now? So there in the first case, right, the initial VSG was 4 volts. Now initial VSG was 5 volts. Now it will be less, it will be 4 volts only. So initial VGSN is 4 volts only, and VSGP is minus 4 volts. So this NMOS will be on and this PMOS will be off. Okay, PMOS will be on, PMOS will be off and NMOS will be on. Okay, so now what will this output voltage go towards? This will go towards all the way up to 4. This will go to all the way up to 4, like as discussed earlier also. So let me just derive it anyways, like we have already derived it. So VGSN should be greater than equals to VTHN, right, VTHN, and VG is 5 volts and this is 1, so should be, it will max go to 4 volts, right. So yeah, we can do this, like this is 1 volts only, this is 1 volts only, and this is 5 volts. So you can do the calculation and you will find that. So this is how the the cycle will repeat, like from mod of VTP it will go to VDD minus VTN, then again it will go down to mod of VTP, and like that it will go. So yeah, what will be the waveform look like? So the waveform will look something like this. Time, and this is, let's say this is V out, right. So the waveform, it will go from 1 volt like this. The charging rate would reduce, it will not charge linearly, and then again it will certainly go down. Okay, this may look like exponential, but this isn't really exponential. Okay, so yeah, this is like this, and like this. Don't go into the totally how the graph looks, because this may look a bit different. Okay, I don't know, but what I try to tell you is that teach you is that basically the VGS and VSG are changing, right. So you should understand that this slope, right, won't remain constant. This will reduce. Here we can see the slope is reducing, right. Here we can see the slope is reducing, going to a zero. Okay, so yeah, so what is this point? This point is mod of VTP. Let me write this, mod of VTHP, and this point, right, is mod of VTHN, right. So yeah, this is this point and this is this point. Okay, this is, so this is how the pulse response will look like. So this video has already gone long, so in the next video we'll do the ramp response and the voltage transfer characteristics of a CMOS buffer. Okay, thank you for watching, and do subscribe to the channel for if you like this explanation, and do hit the like button also. So this helps me understand, yeah, these videos are helping you guys.